Alright, hello everybody and welcome to the outtakes for my integral on the natural log of z over z to the n plus 1 from 0 to infinity. So let's just jump straight in. We want to show that the integral over big gamma and the integral over little gamma both go to 0 in the limits as our r approaches infinity and our epsilon approaches 0. So I've drawn up a quick picture of the contour we were working with in the previous video, and we've evaluated these green lines, so the integral on the real axis and this integral that's going straight down, and now we're just left with the integral over little gamma and the integral over big gamma. And let's take a look at the integral over big gamma first. We want to show that that goes to 0. So we're going to be integrating over our path in gamma of our function f of z dz, and well, that's exactly the integral over gamma. Remember, our function f of z was this function right here that we defined, so natural log of z over z to the n plus 1 dz. And now we have this integral on this curvy path right here. We would like to parameterize that somehow. It would be a little bit nicer that way. So notice that our gamma, or the points in our gamma, we can write them as z, actually not z, what am I talking about? We can write them as r times e to the I theta. Actually, I was right. Z is equal to r times e to the I theta. I'm just thinking of something else today for some reason. So all the points z on our gamma, we can actually rewrite as r times e to the I theta, because this path gamma right here is on a circle, which means that we have this e to the I theta, so all the points on a circle in the complex plane, and we're just scaling that up by r because we have a radius of r right here. And what about this angle theta right here? Well, I'm pretty sure in the previous video that this line right here, this line, is the ray arg of z is equal to 2 pi over n, which means the angle on this path right here goes from 0 up to 2 pi over n. So we have our theta going from 0 to 2 pi over n. Alright, and we have this parameterization. We can differentiate both sides. So dz is equal to I times r e to the I theta d theta, and now we can plug all of that stuff into our integral. So now we have the integral. Now our upper and lower bounds are 0 and 2 pi over n, like so. And then now we have the natural log of this thing right here, because this thing is a z. But notice I'm just gonna do this simplification now because, yeah, just to save some space. This is a product of two things, kind of, r and e to the I theta, and whenever you have a natural log of a product of two things, you can use the natural log property to split it up into the addition of logs. So I'm going to do that in the numerator right here. We're going to have the natural log of our first thing, which is r, and the natural log plus the natural log of e to the I theta. But since we're on the principal branch on our argument, the natural log and the natural log base e can just cancel each other out, leaving us with just this I pi in the exponent. So we have I times pi like so. And all of this is divided by z to the n plus 1. Z is this thing right here, but when we raise this to the n, we can kind of distribute this power into this product right here, giving us r to the n. Then we have e to the I theta to the nth power. We can just multiply this n into the exponent, and we get e to the I theta times n. This plus 1 is still plus 1, and dz becomes I times r e to the I theta times d theta. And now I want to estimate this integral a little bit, because notice this integral, this is still the integral over our path at gamma, and we want to estimate this integral right here to show that it goes to 0 in the limit. So in order to do that, let's take absolute values of this integral right here. So absolute value on our integral. Notice that we can use the integral inequality here because we're actually working with the real variable. Theta is a real variable, which means that the absolute value of this whole integral right here is actually less than or equal to the integral of the absolute value of the inside. So we can kind of bring this absolute value inside of the integral, which means that now we have the integral from 0 to 2 pi over n, and then we're just going to take absolute values of everything inside of here. So first of all, we have the absolute value of this fraction part right here, so natural log of r plus I times theta. That shouldn't be there. So just natural log of r plus I times theta over r to the n times e to the I theta n plus 1. Absolute value of I, that actually just goes to 1. Absolute value of r, well, r is a really big positive number, which means that it's just a constant in terms of theta. We can chuck that out to the front. It can just stay without an absolute value because it's positive. And then absolute value of e to the I theta, well, e to the I theta is every single point on our circle in the complex plane, and all those points have a distance of exactly 1 away from the origin, which means that absolute value of this thing is just, well, 1, so we can ignore it. Alright, very nice. And now what exactly can we do? Let's actually just split the absolute values right here, just to make things a bit clearer. We have absolute values on the top and the denominator, and we're actually going to do two things right here. We're going to use the triangle inequality as well as the reverse triangle inequality at the same time. So triangle inequality, it says that if we have the absolute value of two complex numbers, a plus b, that's actually less than or equal to the absolute value of a plus the absolute value of b. And notice this is nice right here because we actually have the numerator in this form. We have the absolute value of two complex numbers, and we can use this inequality to show that this integral is actually less than another integral, because we're actually showing that this integrand is going to be less than another integrand. So we can use this identity for the numerator, and we can actually use the reverse triangle inequality for the denominator. So the reverse triangle inequality says that if you have the absolute value of a minus b, so instead of having plus we have a minus, this is greater than or equal to the absolute value of a minus the absolute value of b. And you might be saying, well, that's a little bit useless because you're actually showing this thing, or trying to show this thing is less greater than or equal to something else, but we want to bound this thing from above. But in fact, this thing right here, that's on the denominator. We're using this identity on the denominator. So in fact, if you take the reciprocals on both sides, I'll just do it right here. So 1 over everything pretty much. If you take reciprocals on both sides, you're actually flipping the inequality sign. So in fact, if we can get the denominator into this form right here, well, we can use the reverse triangle inequality to show that it's less than or equal to something else. So using the triangle inequality on the numerator and the reverse triangle inequality on the denominator, we can show that this whole entire integral is going to be less than or equal to some other integral. So let's actually just do that. So this integral is less than or equal to, we still have this r right here, we still have our integral from 0 to 2 pi over n, and let's take a look at the numerator first of all. Our a in this case is this natural log of r, and our b is this I times theta. So just plugging it into this identity right here, we have that this integral is less than or equal to the absolute value of a, so absolute value of natural log of r, plus the absolute value of b, which is the absolute value of I times theta, which is just theta. Remember, I is our imaginary thing, so this thing right here is always imaginary, which means that, yeah, absolute value of that is just the imaginary part. So let's see, what else can we do? Notice that r is really big, which means that if we take the limit, this thing right here will just be positive. We don't have to worry about it being negative. Same with our theta right here. Theta is on this interval from 0 to 2 pi over n, which means it's always positive, which means we don't need this absolute value. Alright, now we're going to divide this by the denominator. We have to get this denominator into the form a minus b. We don't quite have it there yet, but we can actually fix that quite easily just by subtracting a -1 instead. That's the same as adding a 1. So now our A in this case is this thing at the start, and our B is -1. So let's use this identity. So now we have the absolute value of the absolute value of r to the n times e to the I theta n. Absolute value of this thing right here, this very term, absolute value of this exponential thing, e to the I theta n, that's going to be 1 because we have I times some real number. Theta n is some real number. So we already know that the absolute value of that is 1. And then we have the absolute value of r to the n. Well, r is a really, really big number, so, well, it's just going to be r to the n. We don't have to worry about absolute values then. And then minus -1, we have a minus absolute value of b. So absolute value of -1, that's just 1, so we just have r to the n minus 1 inside of absolute values, and r is going to grow really big, so a big number minus 1, well, that's still a big number. We don't have to worry about absolute values there. It's quite redundant. So now we can just slap a d theta on the end, and yeah, where can we go from here? Let's rub out this thing right here. I don't really need it anymore. We can go ahead and bring things out a little bit. So first of all, this is equal to r over r to the n minus 1 times this integral from 0 to 2 pi over n of the natural log of r plus theta d theta. And you can see it quite easily already. Once you let r go to infinity, this denominator will overpower this numerator because it's growing at such a faster rate that this thing's going to go to 0. But you also have to be careful about this natural log of r, because as r goes to infinity, well, natural log of r is also infinity as well. So you kind of have to be careful there. Luckily, if you use L'Hopital's rule on this, it does work out nicely, and this thing still goes to 0 anyways. And I'm actually going to do that quickly. Let's use the linearity of the integrals to split this sum up. So now this is equal to, we have r. I'm going to bring up this natural log of r because, well, it's just a constant in terms of theta. So natural log of r over r to the n minus 1. And yeah, we have the integral from 0 to 2 pi over n of d theta. Well, that's just going to evaluate to 2 pi over n. That's really quite an easy integral to evaluate. And then we have plus r over r to the n minus 1. And then we're left with the integral from 0 to 2 pi over n of theta d theta. That's just going to evaluate to some constant. Let's call it, I don't know, eta. Alright, so now if we apply the limit to this thing right here, this thing will definitely go to 0. So this is going to go to 0 in the limit as our r approaches infinity. And how about this thing right here? Well, the top and the bottom both go to infinity if you apply the limit. So we have to use the L'Hopital's rule. So differentiating the top, this is just some product rule stuff. So vu dash, that's natural log of r. And then plus uv dash, well, r times 1 over r is 1, so we just get 1 over, derivative of the bottom is n times r to the n minus 1, like so. And well, you can just split this up further. We're just ignoring this constant right here because it really doesn't matter anyways. So let's see, we can split this up. So this is natural log of r over n times r to the n minus 1. Let's actually just drop this n as well because it doesn't really need to be there. Plus 1 over r to the n minus 1. And just one quick note right here. Our n value right here, this n is some number greater than 2. So even though we have an n minus 1 right here, since n is greater than 2, n minus 1 is still greater than 1, which means that if you apply the limit as our r approaches infinity, this thing, this exponent is still positive, which means that this thing is going to go to 0 anyways. And now we just have this thing right here. Well, top and bottom both go to infinity, so let's use L'Hopital's rule. So derivative of the top, that's 1 over r over, let's see, derivative of this thing is n minus 1 times r to the n minus 2. And, well, it's pretty clear from here. If you just combine this denominator right here, you're going to get an n minus, what was it, 1? I really don't know. But yeah, that's quite clear. N minus 1 is positive, so this thing's just going to go to 0 in the limit. And of course, you have the limit applied to all of these fractions right here. So all of these should have limits as our r approaches infinity. So yeah, overall, what did we just show? We showed that basically everything right here goes to 0 in the limit that as r goes to infinity. So overall, since we actually had all of those inequalities flying around and whatnot, we essentially showed that in the limit, as our r approaches infinity, on the absolute value of the integral over gamma, that's less than or equal to 0. Because remember, when you apply the limit to whatever we had, it's just going to go to 0. But the thing is right here, this is an absolute value, which means it's always positive. And the only way for this positive thing to be less than or equal to 0 is if it's 0 itself. So we have the limit on the absolute value being equal to 0. And what does that say about the actual integral itself? It just implies that the integral itself over gamma in the limit goes to 0. So that's the first integral done. We've showed that the integral over big gamma goes to 0. And now we have our second integral to evaluate. So let's clean things up a little bit here. So our second integral is the integral over little gamma. So let's just change these big gammas to little gammas, like so. Alright, and let's see what little gamma is. Little gamma is just this circle, or this segment of a circle, this arc of radius epsilon. And it's getting traversed in the clockwise direction or negative direction. So if we want to parameterize this path of gamma right here, we can say that all the z's, we know that it's equal to some epsilon times e to the I theta. So e to the I theta gives us the circle of radius 1, and we're just scaling it down to epsilon, where epsilon's going to go to 0 in this limit. So, where does our theta start and where does our theta end? Because remember, theta is our new independent variable. So theta is going to start right up here. So at an angle of 2 pi over n, and it's going to go all the way down to 0. So I'm going to use some weird set notation or interval notation for this. We're going to start at 2 pi over n and go all the way down to 0. So the orientation is kind of reversed right here. This is just to say that we're starting at 2 pi over n and ending at 0. Alright, and what happens, actually, we need to differentiate both sides. So dz is equal to the derivative of this thing, so I epsilon e to the I theta, d theta. And what happens if we plug all of this stuff in? Well, we get the integral. Our bounds become 2 pi over n, all the way up to 0, of the natural log of z. But remember, z is this thing, and I'm going to do what I did before. We're going to use this natural log property to split this product into a sum of natural logs. So first of all, we have the natural log of epsilon, and then plus the natural log of e to the I theta. One, the principal branch, so natural log and e will cancel each other out, leaving us with just an addition of I times theta. And all that is divided by z to the n. But z is, remember this thing, raising that to the nth power, we're going to get epsilon to the n times, not epsilon, we're just going to get e, so e to the I theta times n. We still have this plus right here, and our dz becomes I epsilon e to the I theta d theta. Alright, so this is our integral over gamma. And what would happen if we take the limit as our epsilon approaches 0 on the integral over gamma? Well, we can kind of bring the limit inside of the integral. I know you have to use like dominated convergence theorem or something like that. I don't know much about that stuff yet, so we're just going to assume that we can interchange those two limits right there, because it just works out nicely in the end. That's my proof, I guess. So yeah, if we drag this limit inside of this integral right here, what are you going to get? You're going to get the integral from 2 pi over n to 0. First of all, let's actually just apply the limit step by step, kind of. If this epsilon goes to 0, this whole thing is going to go to 0, leaving us with just the division by 1, which just leaves us with this numerator, so natural log of epsilon plus I times theta. Then we still have this stuff hanging around up here, so I epsilon e to the I theta and d theta. And you could plug epsilon equals 0 into here to kill off the whole thing, but you also have to be careful about this natural log. Also, we still have the limit hanging around because we haven't applied it to everything yet. I guess the best way to go about this is just to expand everything out, split the integral using the linearity and all that. So now we have the integral from 2 pi over n all the way up to 0. Limit as our epsilon goes to 0. This thing, natural log of epsilon times all this stuff right here. So natural log of epsilon times I times epsilon times e to the I theta d theta. And then now we have a plus integral from 2 pi over n to 0. Limit as epsilon goes to 0 of this second part right here, which is I times theta times another I times epsilon times e to the I theta d theta. This integral obviously goes to 0 because as this epsilon gets smaller and smaller and smaller, it's just going to kill off the integrands and it's just going to end up with a 0. And the main thing we have to worry about on this integral is this natural log and this epsilon right here, both approaching 0, because this natural log is going to go to negative infinity. So let's actually just, let's just focus on the limit as our epsilon goes to 0 on the natural log of epsilon times epsilon. Let's just focus on those two parts multiplied together. What exactly is this limit going to evaluate to? Should go to see it now. This limit, we can't evaluate it using L'Hopital's yet because we have infinity times 0. Ideally, we want like infinity divided by infinity. Luckily, what we can do is we can just divide by 1 over epsilon, because this epsilon can just flip back up to the top and we get your epsilon back. So now in this case, in the limit as epsilon approaches 0, this is going to go to some kind of infinity, and this is going to go to infinity as well. So everything works out there. And applying L'Hopital's, we're going to get the limit as our epsilon approaches 0 of derivative of the top is 1 over epsilon, derivative of the bottom is negative 1 over epsilon squared. Flipping this epsilon squared back up to the top, you're going to get negative, so this is equal to negative the limit as epsilon approaches 0 of epsilon squared over epsilon. Well, that's negative, or don't even need to worry about the limit, the negative anyways, the limit as epsilon goes to 0 of just epsilon itself, which is just a 0. So this limit right here actually just evaluates to 0, which means that this integrand goes to 0, which means that in the limit as our epsilon goes to 0 of our gamma right here, that's just going to be 0. Alright, so we've shown that both of our integrals over big gamma and little gamma both go to 0, and that should complete the whole entire proof for the whole entire video on this integral, I guess. So yeah, hope you guys enjoyed it, and I'll see everyone next time. Bye bye.